Morning all. So in this lecture we will see about analytic functions and harmonic functions. Show that the real and imaginary parts of analytic function or harmonic function. So given that f of z equal to u plus iv is an analytic function. So when f of z is an analytic function, it satisfies the CR equations ux equal to vy and uy equal to minus vx. That is dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. Now you just name it as equations 1 and 2. You differentiate equation 1 with respect to x on both sides. So when you do that, what you will do, you will be differentiating this with respect to x like this. So when you do this becomes dou square u by dou x square. This side it becomes dou square v by dou x dou y. So this is equation number 3. Now you differentiate equation 2 with respect to y on both sides. So when you do that, this will be dou by dou y of dou u by dou y and dou by dou y of dou minus dou v by dou x. So this side becomes dou square u by dou y square. This side it becomes minus dou square v by dou y dou x. So name it as equation number 4. Now we will prove u is harmonic and v is harmonic. So here we are trying to prove u is harmonic. So you add equations number 3 and 4. When you add this side, so you have dou square u by dou x square plus dou square u by dou y square. This side when you add, here the mixed partial derivatives like dou square v by dou x dou y and dou square v by dou y dou x both are same. So when you add here it is positive and negative, so it gets cancelled leaving out 0. So you have dou square u by dou x square plus dou square u by dou y square equal to 0. That means u double x plus u double y equal to 0, which is del square equal to 0, which is the Laplace equation. So u is harmonic. Now we want to prove V is also harmonic. To do that, you take again equation 1 and 2. In equation 1 and 2, now what you are going to do, you differentiate this equation 1 with respect to y and 2 with respect to x. Just what we have done here, the opposite way. Here we have differentiated with respect to x and y, but here we need to differentiate with y and x. So when you do that, this v dou by dou y of dou u by dou x, and this will be dou by dou y of dou v by dou y. So here you can see clearly this side dou square v by dou y square. This side it is dou square u by dou y dou x. So that is what I have written here. So name it as equation number 5. Now what you do, you take equation number 2 and differentiate with respect to x. So it is dou by dou x of dou u by dou y and dou by dou x of minus dou v by dou x. So this side it is minus dou square v by dou x square. You pull out minus. This side it is dou square u by dou x dou y. So that is what I have written here. Okay. So we obtained two equations, equation number 5 and 6. So what we are going to do, we need to prove that dou square v by dou x square plus dou square v by dou y square equal to 0. But here you have minus dou square v by dou x square and dou square v by dou y square. So you just subtract equation 6 from 5. So when you do that, this term minus minus this term becomes plus. So we are going to use 5 minus 6 otherwise. Okay. So that's what I've done here. So this side what happens? You have dou square u by dou y dou x minus dou square u by dou x dou y. This side it is dou square v by dou y square minus minus dou square v by dou x square becomes plus here. So we have this side and the other side this gets cancelled, so leaving out 0. So you have dou square v by dou x square plus dou square v by dou y square equal to 0, which is v double x plus v double y equal to 0, which gives del square v equal to 0, which is a Laplace equation again with respect to v. So v is harmonic. And there is a note, u and v of an analytic function f of z equal to u plus iv are called conjugate harmonic functions of each other. That means u and v are said to be conjugate to each other with respect to the harmonic functions if f of z is analytic. Thank you. Good morning. Show that an analytic function with constant modulus is constant. We are going to prove this result. Now let us take, we know f of z is u plus iv, right? Now take modulus for this, that will be modulus of u plus iv, which is going to be a constant they are telling here. Okay, so that's what I have written here, where f of is an analytic function. Now modulus, when you take this u plus iv modulus, this is nothing but like square root of u square plus v square, which is constant, or u square plus v square equal to constant. Name it as equation number 1. Now we need to prove that this analytic function with constant modulus, okay, is going to be a constant. So how will you prove that? Let us take this u square plus v square equal to constant. Now differentiate this. We have named it as equation 1. Differentiate 1 with respect to x partially on both sides. So this is dou u 2u into dou u by dou x plus 2v into dou v by dou x equal to 0. So because we are differentiating it, so 2u dou u by dou x plus 2v dou v by dou x equal to 0. Now take 2 common, so that means there won't be 2 here. So u dou u by dou x plus v dou v by dou x equal to 0. Now again you differentiate equation 1 with respect to y. So 2u into dou u by dou y plus 2v into dou v by dou y is 0. Again, when you take 2 common, so you get u dou u by dou x plus v dou v by dou y equal to 0. Dou u by dou y plus v dou v by dou y equal to 0. So you get equation 2 and 3 here. Now with this, what we can do? Since f of z is analytic, CR equations are satisfied. So what are CR equations? Dou u by dou x equal to dou v by dou y, dou u by dou y equal to minus dou v by dou x. So take these equations, try to substitute in equations number 2 and 3. So here I'm going to substitute in equation 3. I'll tell you the reason why. So here dou u by dou y, that becomes minus dou v by dou x. So here in place of this I am substituting minus dou v by dou x, and dou v by dou y, that is vy, which is ux, as you know. So I'm going to substitute here ux. So when you do so, you get these two terms getting replaced by CR equations, and you get v dou u by dou x minus u dou v by dou x equal to 0. So this is like equation number 4. So why do we need this equation? So what I'm going to do here is I will just take equation 2. So I will try to multiply equation 2 by u, and I will take equation 4 and multiply this equation 4 throughout by v. So when you do so in equation 2, when you multiply by u, this becomes u into u square, here u into v. So that is what I wrote it here. Where is that? Here. Okay. And then when you multiply v here, it is v square and vu or uv. After doing that, I have just added. Okay. So I have added this two. So why I'm going to add? Because this uv dou v by dou x and minus uv dou v by dou x is cancelled, leaving out u square plus v square into dou u by dou x, which is equal to 0. Since u square plus v square is not equal to 0, dou u by dou x is 0. And you just keep this. Now what you go with equation number 2 again, multiply this now with respect to so with v. Okay, so v u and v square you get. Okay, and equation 4, previously we multiplied by v, you remember. Now we will multiply v by u. Okay, so u v and u square. So this is what I have done here. And after doing this, what I'm going to do, I subtract that equation 4 from 2. That means 2 minus 4 after multiplying by this v and u. Okay, so when you do that, what is happening here? You can see very well uv dou u by dou x and minus uv dou u by dou x gets cancelled, and you also have this v square plus u square into dou v by dou x, which is equal to 0. Since v square plus u square is not equal to 0, this dou v by dou x is 0. So we got dou u by dou x is 0 and dou v by dou x is 0. So we know very well that f dash of z is ux plus ivx, that is dou u by dou x plus I into dou v by dou x. And as we proved that ux is 0, that means dou v by dou x is 0 and vx is 0, that is dou v by dou x is 0, both are getting 0. Therefore f dash of z is 0. That means your f of z, when you integrate on both sides, f of z is a constant. So whenever you have the modulus of the analytic function is constant, we have proved that f of z is also constant. So that is the proof. Thank you. Hi all, good morning. In today's lecture, we'll show that an analytic function whose real part is constant must itself be a constant. So let us take the analytic function f of z equal to u plus iv. Since f of z is analytic, it satisfies the CR equation dou u by dou x equal to dou v by dou y, and dou u by dou y equal to minus dou v by dou x. And they're telling that u is constant, that is u of x comma y is constant. If u is constant, then we need to prove this f of z is constant. Okay, so that is the proof. Since u is constant, when you differentiate partially with respect to x and y, dou u by dou x becomes 0, dou u by dou y becomes 0. And also we know that by CR equation, uy equal to minus vx. That means I'm replacing dou u by dou y equal to minus dou v by dou x. That is dou v by dou x is also 0 because uy is 0, vx is 0, right? And also ux is 0. Okay. And also we know that f dash of z is ux plus ivx. That is dou u by dou x plus I into dou v by dou x. Since this u x and vx, that is dou u by dou x and dou v by dou x is 0, f dash of z is 0. Therefore, when you integrate on both sides, f of z is a constant. So here what we have proved, u is a constant, then f dash of z is 0 and f of z is a constant. Okay, u is a constant, then f of z is a constant, right? So this is what we prove. Now we will show this result. Take imaginary part is constant and we will prove f of z is constant. So the same case, f of z is analytic, it satisfies CR equation. Since imaginary part is constant, now v is getting constant, right? So v of x comma y is equal to constant. Now you you can see here dou v by dou x is 0 and dou v by dou y is 0. How it is done? Because when you differentiate v with respect to x partially, dou v by dou x is this side is constant, constant differentiation is 0. In a similar fashion, we get dou v by dou y is also 0. Now we know from CR equations ux equal to vy, which is 0. Therefore, we change this vx as vy as ux. So you get dou v by dou x here. So what I have done here is f dash of z equal to ux plus I vx. So dou u by dou x plus I into dou v by dou x. We know very well that this ux is this dou v by dou y, which is 0. So I am replacing this ux as this vy, which is 0, and vx is also 0. We know that. So we have 0 plus I 0, which is 0. Therefore, f dash of z is 0, and when you integrate on both sides, f of z is a constant. That means if v is a constant, then your f dash of z is 0, and you get f of z is a constant. So we have proved these results. Thank you. Very good morning, all. Today's lecture we will see about the orthogonal conditions for analytic function here. If f of z equal to u plus iv is an analytic function, then the family of curves u equal to c1 and the family of curves v equal to c2 cuts orthogonally, where c1 and c2 are varying constants. So we'll take f of z, which is analytic, that is u plus iv is analytic. It satisfies the CR equation here. Okay, sorry, it satisfies the CR equation ux equal to vy and uy equal to minus vx. Name it as equation 1. Now, given that u is a constant, okay, given that u is a constant, so here what I'm going to do, since u is a function of x and y, now we'll just have this x and y again. You just make it as a function of x. That means we need to get a result like dy by dx, right? So you differentiate u with respect to x partially. So dou u by dou x into dx by dx, this side, plus dou u by dou y into dy by dx. Because we need dy by dx, we have, because x is a function of x, again y is a function of x, so it is a single variable, so you have to write as dy by dx, not dou y by dou x. Okay, so this gets cancelled, so you have dou u by dou x, and this side it is same. Now we need dy by dx, right? So keep this one side and take this to other side. So minus dou u by dou x. Now I need dy by dx. Therefore, you just divide this here. So you have minus dou u by dou x by dou u by dou y. Let us name it as equation. Sorry, let us name it as m1, and even you can name it as equation 1, 2, but no problem. So you just have dy by dx as m1, right? So here this represents the slope of family of curves u of x comma equal to c1. Now take v equal to c2. Now again v is a function of x and y, and this x and y are functions of x. When you take like that, then we need dy by dx, right? So dou v by dou x into dou x by dou x plus dou v by dou y into dy dy by dx, sorry, dx by dx and dy by dx. So this gets cancelled. So dou v by dou x plus dou v by dou y into dy by dx. Now you keep this, take this to other side, which is minus dou v by dou x. Now you divide this here, so you get dy by dx is minus dou v by dou x by dou v by dou y. Let us name it as equation 3, or just you can have it as m2, which is going to be equation 3. So if you want, you can name it as equation 2 here and equation 3 here, right? So which is m1 and m2, right? This second equation represents the slope of family of curves v of x comma y equal to c2. Now you know the orthogonal condition m1 m2 should be equal to minus 1. So we had to prove that. Take m1 is first equation, sorry, second equation we have. So m1 is this minus dou u by dou x by dou u by dou y. m2 is m2 is minus dou v by dou x by dou v by dou y. So multiply this together. So when you do that, again I just want to cancel this term. So this one I'm not touching, as such it is, but this one will make use of CR equations. So this dou v by dou x becomes dou u by dou y by CR equation. U equal to vx minus sorry, ux equal to vy and uy equal to minus vx. So this full quantity becomes uy, right? Because uy is minus vx, and this vy, ux and vy are same. Okay, so I replace this by vx. This negative completely has been replaced by uy. Okay, so you know very well now we need to get minus 1, right? Because you have negative dou u by dou x, and here this positive, it gets cancelled. I mean, this negative term is left out, so this is cancelled and this one gets cancelled. So you have minus into 1, which is minus 1. So we have proved m1 m2 is minus 1, hence both the families of curves cut orthogonally. Thank you.